Good afternoon, class. We are looking at exam 2 review, chapter 3, differentiation rules. And here's part 3, covering 3.6, derivatives of the logarithmic functions. (3.6) Derivatives of the log and inverse trig functions. Y equals ln x. We want to take the derivative. We go to the definition, e to the power of y equals x. That's the definition of a log. And now we are going to differentiate both sides implicitly. The derivative of e to the power of y is e to the power of y, because we know the exponentials, times y prime or dy dx, and x gives us 1. Divide both sides by e to the power of y or x, so y prime or dy dx is 1 over x. So y equals ln x. Its derivative, simply flip it over. And that's the proof using implicit differentiation. So d dx of ln of absolute value of x is 1 over x. X can't be 0. The reason we put absolute value, because, as you know, the domain of our natural law is 0 to infinity. If instead of x we have g of x, according to this we flip it over, and according to the chain rule, times g prime of x. Sometimes g of x or u are used. U represents g of x, so 1 over u du dx. Let's remind everyone of logarithmic properties. If b is larger than 0 and it's not equal to 1, then y equals log x base b is equivalent to x equals b to the power of y. We're talking about here. So as you look at this one, look at the arrow. B to the power of y is x. If we can make this transition from one format to the next, we are in good shape. It gives rise to the properties of logs for general case, any base b, as long as it's positive and not equal to 1. Log 1 is 0, because you can look at this arrow. Log b base b is 1. Log b to the power of x of base b is x. B to the power of log x base b is x. Log of x y is log x plus log y. All of them same base b. Log x over y is log x minus log y. All of them base b. And log of x to the power of n is n log x. Both sides have the same base. We've gone through that before, and you should be very comfortable with logarithmic properties. Now, when we go to common log, log x base 10, we don't write the base. We just write log, and that means common log. The base is 10. Therefore, instead of b to the power of y, we have 10 to the power of y equals x, giving rise to those properties. And I hope we can make the transition from here to here. One thing I want to make a point of, log b base b equals 1. These two must be the same. When you don't write the base must be 10, so log 10 must be 1. Log b to the power of x base b is x, and in this case, log of 10 to the power of x is x. B to the power of log x base b, b, we know it to be 10, so 10 to the power of log x is x. And again, this is the product rule, the quotient rule, the power rule. Extended to natural log. In the case of a natural log, the base is e. So instead of saying log x base e, we're going to write ln(x). That means the same thing. So b to the power of y equals x becomes e to the power of y equals x. And Here's the properties, ln1 equal to 0, and the rest of them, just as an example again. Log b base b, when we go with natural log, the base is e, so ln e is equal to 1. Log b to the power of x, when the base is b, you're going to write ln e to the power of x, because the base is e when you say l, n, and the rest of it follow as well. Exponential functions, logarithmic functions, are inverse functions, therefore symmetric with respect to the line y equals x. We also have the change of base formula. Log x base b is log x over log b with any base, for example, a. Normally we use common log or natural log. So we showed the derivative of ln x is 1 over x, and therefore g of x by the chain rule becomes 1 over g of x times g prime. If you happen to have a different base instead of e, then according to logarithmic properties, we tag along 1 over ln b. We'll discuss this further as we come across it. We want to differentiate y equals 1/2 ln of 1 plus x over 1 minus x. There are two ways to do that. One is just the way it is. You have the 1/2. You flip this over, and then you take the derivative of that using the quotient rule. You don't want to go that route because that is much more difficult. So the best course of action is to know and remember logarithmic properties. So as you look at this one, you should know that you can use the quotient rule. So ln of the top minus ln of the bottom, and you keep the 1/2 outside. And now it's a lot easier. So we are using number 6, which is the quotient property. Now 1/2 remains. Ln of 1 plus x. You flip this over. 1 over 1 plus x. And then times the derivative of the parentheses 1 by the chain rule. This one minus, flip this over. And the chain rule says we need the derivative of the parentheses. So times, what is the derivative here? -1. And so we are going to take a common denominator of 1 plus x times 1 minus x. Please understand this is 1, everybody. This is 1. And this is plus 1, okay? So 1 times 1 minus x plus 1 times 1 plus x. And the denominator, of course, 1 plus x times 1 minus x. So you keep the 1/2. You come up with the LCD, the least common denominator, or just simply common denominator, 1 plus x times 1 minus x, 1 times 1 minus x, and 1 times 1 plus x belong to the numerator. All you have to do is simplify the numerator. One minus x plus 1 plus x. These two cancel each other, and the numerator is 2. This one cancels out this one, and we get 1 over 1 minus x squared, because the product of these two is 1 minus x squared. Y equals ln of sine theta. We flip it over. 1 over sine theta. and then by the chain rule times the derivative of sine theta, which is cosine. Now cosine theta over sine theta is cotangent theta, and we are done. Y equals e to the power of x over 1 minus e to the power of x. We use the quotient rule. Which is f prime g minus g prime f over g squared. So let's call the numerator the f function, the bottom the g function. And so f prime is simply e to the power of x times g, which is just the denominator, 1 minus e to the power of x, minus g prime. What is the derivative of the bottom? E to the power of x is itself, and just keep the sign. So minus e to the power of x, and then times f, the top is e to the power of x. Finally, g squared. Just write the same thing here, put it in a parentheses and square it. Now it's just a matter of simplification of the numerator. So this is e to the power of x. When you multiply these two, you get minus e to the power of 2x. When you multiply these two, say plus e to the power of 2x. I hope you recognize e to the power of x, e to the power of x. You add up the x and x, you get 2x. These two are opposite. So you're left with e to the power of x. Okay.
Professor, could you remove the EX could you factor it out of the whole thing and then set it up that way? Like, would that be a good answer?
No, because it's easier to get rid of these two first. Just get rid of these two. If you factor the e to the power of x, the same thing happens, but it's just an extra step.
Okay.
Does that make sense?
Yeah.
Do you know what I'm talking about? I mean, you could factor it out, but it doesn't help. It doesn't make it any easier. That's the bottom line.
Okay. All right.
All right. Again, the question was, could we factor out e to the power of x? Yes, if you factor out e to the power of x, you get e to the power of x times 1 minus e to the power of x plus e to the power of x. These two cancel out, you don't need to. All right, we're going to try y equals ln of 5x. And let's see what happens here. Well, first we flip this over. So understand that ln of 5x is the argument of n. According to this formula, flip over the argument. So 1 over ln of 5x. Now we want to go to g prime. Now we are going to work on this piece and differentiate it. So you can, if it helps, just call it g of x. Okay. So 1 over g of x or 1 over ln of 5x. Now we want g prime of x. Now what is the derivative of natural log of 5x? You flip this over. And then times, by the chain rule again, the derivative of 5x, which is 5. So I hope you see that this is the derivative of ln 5x. In other words, this part is g prime of x. You rewrite this. First of all, you're going to get rid of the 5, and then you rewrite it, okay, in this form. 1 over x ln of 5x. We gotta move on. We want to differentiate y equals log base 3 of square root of x. So we are going to show how we differentiate log when the base is no longer e, and here's the proof. Log x base b based on change of base formula is ln x over ln b. Change of base formula, which means 1 over ln b times ln x. What I want to make a point of, these two are identical, and this is just a number. Bear in mind, this is just a coefficient of ln x, a number. 1 over ln b is a number. When you keep it as ln b, it's an exact answer. So if you want to differentiate this, well, you keep this and flip this over. And when you rewrite it, the reason you put the x in front, because if you put it afterwards, one may read it as ln of bx. That's why we put the x in front. So that's how you do that. So first thing first, you write this as x to the power of 1/2. Then we bring the 1/2 in front using the power rule, this one. Now we are ready to differentiate. So we keep the 1/2. So y prime equals, we keep the 1/2. We are dealing with logs. We flip this over. 1 over x. We look at the base. If the base is e, we're done. It's not 1 over ln b. 1 over ln b. So 1 over ln 3. Now we put them all together. We write it as 1 over 2x ln 3. F of x is log base 5 of x squared plus 1. So basically, if the base is not e, we follow this format. And then if it happened to be a function, we follow the chain rule. So you want to take the derivative of log of f of x base b. You are going to flip this over. This is the derivative of logs. You're going to multiply by the derivative of f prime by the chain rule. This is the chain rule. And then because the base is not e, 1 over ln b, this is by logarithmic properties. And now you put them together in this format. So we're going to do exactly the same thing here. First, here's the function. We flip this over. 1 over x squared plus 1. Then this is not x, it's a function of x. We need its derivative based on the chain rule, so we need 2x. Since the base is not e, we need 1 over ln of the base, 1 over ln 5. That's this one. Put them together. 2x over x squared plus 1 ln 5. Again, if you put that after 5, one may read it as ln of 5 times that, which is not true. All right, we want to take the derivative y equals ln 5x over x squared plus 5. Differentiate. Well, the best course of action is to decompose the log. It makes it easier rather than flipping this over and then taking the derivative using the quotient rule. It takes a lot longer if you don't see the easy way out. The long way, most likely you won't see the answer either. This is ln of the top minus ln of the bottom. You don't have to do it in 2 steps, but I'm going to show you. This is ln of the top minus ln of the bottom, and ln of the top is ln 5 plus ln x. So you have decomposed the log completely. Now you're ready to move on. This was logarithmic properties, had nothing to do with calculus. ln 5 is a number. Its derivative is 0. So y prime equals 0. I'm going to put 0 on purpose. ln x is 1 over x minus, now ln of this expression, 1 over this expression, which is x squared plus 5. And then by the chain rule, I need the derivative of that, which is 2x. And I'm done with calculus class. This is my only calculus step. Now I need to use my algebraic techniques to finish the job. Again, done. Calculus is done. I put the asterisk next to it. And I want to emphasize this because prior knowledge of mathematics makes a difference. So the common denominator is x times x squared plus 5. And so we have 1 times x squared plus 5 minus 2x times x. So we are going to write the common denominator. Then 1 times x squared plus 5 minus 2x times x minus 2x times x. This is important to see, okay? Minus 2x times x. We are going to simplify the numerator and we get x squared plus 5 minus 2x squared. These two combine into negative x squared. We are done. Part B, g of x equals log of 9 minus x cubed to the power of 4. We want to differentiate any logarithmic format. The first step is, can I simplify it using logarithmic properties? I bring the 4 in front using the power rule. There's nothing else I can do to simplify it further. Remember this, there's no way to simplify it. So now we are going to differentiate as follows. G prime of x is 4 times, flip this over, 1 over 9 minus x cubed. By the chain rule, I need the derivative of this piece, which is negative 3x squared. I look at the base. The base is not e. In fact, it's 10, 1 over ln 10. I'm looking at this part, everybody. 1 over ln 10. That's how you do it. Okay, it's very straightforward. I hope everybody is fine with that. Put them together. 4 and negative 3x squared belong to the numerator, negative 12x squared. and these two belong to the denominator. Find an equation of a tangent line when y is equals x squared ln x at 1, 0. In order to come up with an equation of a tangent line, you need two things. You need the pair. In fact, you need the x because you plug in x and you get y. If you plug in 1, you get 1 squared times ln 1, which is 0. That's how you get 0. You need this slope. To find this slope, we are going to differentiate first y prime or f prime of x. To do so, we notice this is x squared times ln x. We put a raised dot and we call this f times g, and we use the product. You learn that. F prime is 2x times g ln x plus g prime 1 over x times f, which is x squared. And all you have to do, simplify this into x. That's all I mean. There's nothing else we can do. So this is y prime or f prime of x. The slope of the tangent line at x equals 1 is y prime evaluated at x equals 1. So let's plug in 1. We get 2 times 1 ln 1 plus 1. As you know, ln 1 is 0, so the answer is 1. So y minus y1 equals m times x minus x of 1. That means y minus 0 is 1 times x minus 1, which means y equals x minus 1. Differentiate where y equals log base 3 of 1 plus theta ln 3. The first thing is, can I simplify the log using logarithmic properties? The answer is no. Therefore, y prime, or better yet, dy d theta, because I want you to read and notice that theta is the independent variable. So we should really call it dy d theta, so we are telling our readers what variable is the independent variable. If you said y prime, there is nothing wrong with that. Y prime or dy d theta is, flip this over. By the chain rule, we need f prime of x. In this case, we need the derivative of theta here. This gives you 0, this gives you ln 3. Please understand the derivative of this argument is the number ln 3. ln 3 is just a number. Okay. Finally, is the base E? No, so you need 1 over ln 3. I'm looking at this one, 1 over ln v. So I need 1 over ln 3, and these two cancel each other. Here's the final answer. Pretty straightforward, everybody. By the way, just recall that, I mean, this is another way of doing it. If you go back to the change of base formula, log base 3 of 1 plus theta ln 3 is ln of 1 plus theta ln 3 divided by ln 3. This is by the change of base formula. You could have tackled it that way. Again, properties of logs, they play a huge part. Y equals ln of 2 e to the power minus t sine t, and we are going to simplify this first before we do differentiation. Natural log of this times this times this. So we are going to use the properties of logs, in this case, the product rule, to decompose. We are going to use the product rule to decompose the log. So this is ln of 2 plus ln of e to the power minus t plus ln of sine t. This has got nothing to do with calculus, everybody. We are completely decomposing the log. We are completely decomposing the log. So there is one more step. Notice this part is just negative t. ln of e to the power of x is x. ln of e to the power minus t is minus t. Now let's work on it one by one. So we want to differentiate. Now we are going to differentiate this one. ln 2 is a number, the answer is 0. This part is negative t, the answer is negative 1. This part is ln of sine t, flip this over, 1 over sine t. By the chain rule, we need the derivative of the expression sine t, which is cosine t. So this is minus 1. Cosine over sine is cotangent t, and we are done. Again, it's pretty straightforward, everybody. You should be very comfortable with logarithmic properties to make sure this is easy to handle. We're going to continue differentiating. Y is equal to t log base 3 of e to the power of sine t ln t. Again, remind you that ln of e to the power of x is x, e to the power of ln x is x. So we are going to interchange these two. So we're going to put this one first. Remember, the exponent here is the product of two things, sine t times ln 3. So we're going to put ln 3 first. It makes no difference. So I'm just rewriting. I'm not doing anything yet. I'm rewriting this by putting ln 3 next to e. So what happens? E to the power of ln 3 Let's go here. E to the power of ln x is x. E to the power of ln 3 is 3. So this thing can be replaced by number 3. Now, t times log base 3 of 3 to the power of sine t. You just bring the sine t and you say, this is 1, by the way. You can do it in 1 or 2 shots. If you want to do it in 2 shots, bring the sine t in front. And this one is 1, everybody. Because the base and the arguments are the same. So let's rewrite the function y has simplified to t times sine t, which requires the product. F prime g plus g prime ft gives you 1 times the sine t. You can say dy dt. And again, you can write y prime because the independent variable is t. I rather write dy dt. I want to let the readers know that it's dy dt. The t is the independent variable. It's not dy dx. So 1 times sine t plus sine gives you cosine t times t. And you rewrite this as sine t. And you bring the t in front. It's extremely important that you do so because we don't want anybody, I've seen this mistake, we don't want anybody to think this is cosine of t squared because it's not. So make sure you do that. All right, we are going to move on. Logarithmic differentiation. Y equals x to the power of 3/4 square root of x squared plus 1 over 3x plus 2 to the power of 5. Generally speaking, when the function is a complicated function, we use what's called logarithmic differentiation. So what is logarithmic differentiation? Step 1, take natural log of both sides. So if I take the natural log of this side, this is ln y, and this one I can cut it into pieces. And I'm going to do it in one shot. I hope everybody can follow that. First of all, it's ln of the top minus ln of the bottom. Ln of the top is ln of this plus ln of this, which is the power of 1/2, by the way, minus ln of that. So again, you can do it in 1 or 2 shots. So ln of the top minus ln of the bottom. So ln of the top, maybe let me write this step in case. So the first step is ln of the top minus ln of the bottom. So that's, let's say this is step number 1. Let's say this is step number 2. Okay, we are taking natural logs, and this means a lot of simplification. So what happens here? 3/4 sits in front. What happens here? 1/2 sits in front. What happens here? 5 sits in front. Now, this one, and this one, which means now we are done with decomposing the log completely. So the second step is to differentiate implicitly with respect to x. Now we are going to differentiate. Again, if you go back to the original one, it was extremely difficult. Ln y, as you know, it's 1 over y times dy dx. So you flip this over times y prime or dy dx. Implicit differentiation, everybody. Ln y, the derivative is 1 over y. And y is like g of x. It's a function of x, dy dx. The reason we know it's a function of x, on the right side, it says x, okay? All right, now 3/4 times 1 over x. This one is plus 1/2 times, flip this over, 1 over x squared plus 1, and then times 2x, okay? Times 2x, everybody. This is by the chain rule. This is by the chain rule. Minus 5, and flip this over. So minus 5, flip this over, and then times the derivative of the inside, which is 3. So that's how you do that, everybody. Again, it's pretty straightforward. I hope everybody's following that. Now, the next step is to multiply the right side by y. So basically move 1 over y. But before we do that, this is 3 over 4x. This is x over x squared plus 1. This is minus 15 over 3x plus 2. So one more time. You simplify this one to 3 over 4x. You simplify this into x over x squared plus 1. This one minus 15 over 3x plus 2. And you just take 1 over y to the other side. How do you take it to the other side? Multiply by 1. So solve for dy dx. And so replace the y with this expression, and you're done. It's that simple, everybody. Okay? I hope everybody is following what happened. It's pretty straightforward. So let's quickly recap the steps, making sure we know what we are doing. Step 1, you take a log and decompose completely. When do we do that? If they ask for logarithmic differentiation, or if you come across something which is very difficult to do so. Take a log, use logarithmic properties to decompose completely. Now take the derivative of both sides and you do it, differentiate it implicitly. This will flip over and then times dy dx, and the right side, you follow logarithmic rules of differentiations. Then the next one is to get rid of 1 over y. You just take it to the other side and we multiply. Please see what happens to it. You take 1 over y to the other side and you multiply it by the whole parentheses, by the way. Okay? So it's pretty straightforward. We're going to do the same thing. If by any chance you have a format that the base and the exponent are both functions, also you have to use logarithmic differentiation. In this case, even if they don't tell you, there is a different method also, but let's go with logarithmic differentiation. number one, take the natural log of both sides. So if I take the natural log of the left side is ln y, okay, take a natural log. And this one, sine x, ln x. So ln x to the power of sine x, okay, ln of x to the power of sine x, and sine x sits in front, becomes the coefficient, okay? All right, so what happens next? Now we are differentiating implicitly, which means we are going to flip this over and then times y prime. 1 over y times y prime. The right side is a product of two things, so you use the product rule on that. Let me write f times g. So we need f prime. Sine gives you cosine times ln x plus ln x gives you 1 over x times sine x. I'm using the product rule. We are done. Basically, we are done. The right side is cosine x ln x plus 1 over x sine x or sine x over x. You multiply both sides by y, or you just move it to the other side. That means multiplication. So you solve for y prime or dy dx by moving this, by multiplying by y. So we are multiplying by y. And you just replace the y with whatever you had up there. This is an important step. You have to replace it. So y prime is x to the power of sine x, parentheses cosine x ln x, plus you can say 1 over x sine x or sine x over x, makes no difference. Mostly we do by logarithmic differentiation. There is a different method, I mentioned it, and you can finish it at home. And that's the way you would rewrite this, such that the base is no longer variable x. So recall e to the power of ln x is x. So y equals x sine x. We are going to replace the x with e to the power of ln x. X is the same as e to the power of ln x. And so therefore, e to the power of the product of these two, ln x times sine x. And you can, I highly recommend you try this. You differentiate this one, you get to the same answer, everybody. Okay, you can try that. Derivatives of inverse trigonometric functions. The derivative of sine inverse is 1 over 1 minus x squared. The derivative of tan inverse is 1 over 1 plus x squared. The derivative of secant inverse secant function is 1 over x square root of x squared minus 1. The rest of them are basically the same with a negative sign in front of it. So cosine inverse, the derivative of cosine inverse is the same as sine inverse, but 1 becomes negative 1. The derivative of cotangent inverse is the same as tan inverse, 1 becomes negative 1. The derivative of cosecant inverse, the same as secant inverse, 1 becomes negative 1. Recall, sine inverse of x equals y by definition means sine of y is x. Okay. The trigonometric functions, none of them is 1 to 1. And we had to restricted domain, in the case of a sine, we restricted from negative power to 2 power 2. That's the domain of sine x, or the range of sine inverse. And sine inverse of sine x equals x, sine of sine inverse of equals x. As long as, in this case, we pay attention to sine x, x must be between negative power 2 and power 2. As we go to sine inverse here, sine inverse, then x must be between negative 1 and 1, because domain becomes range, and range of sine, which was negative 1 to 1, becomes the domain of its inverse. As far as cosine, if you recall, cosine inverse cosine x is x if x is between 0 and pi. The restriction we put for sine was the fourth and first quadrant to make sure the range of negative 1 to 1 is covered. For cosine, we said 0 to pi, the first and second quadrant. This is from trigonometry. Cosine of cosine inverse of x equals x, where x is between negative 1 and 1. And so those are the synopsis of everything we discussed. What I just want to add is this. What if instead of x, we have g of x or u? Then the numerator, 1 is the derivative of x, everybody. So you put du dx. And then 1 minus x squared becomes 1 minus u squared. If you call it g of x, the top is g prime, and this is g of x squared. If you go with this on purpose, I use u here and I used g of x here. So if you have g of x, so this numerator 1 is the derivative of x, becomes g of x. This is g prime of x, not g prime of x. I thought it's g prime, but it probably is not showing g prime. This is g prime, everybody, okay? And over here, we have 1 plus x squared. So the x is the function g of x now, 1 plus g of x squared. Okay, just wanted to make sure that you see that. Now, we have this from the previous page, and we are going to look at the proof. We know the derivative of sine inverse is 1 over 1 minus x squared. So let's take a look at some proof, for example, for sine inverse. So let y represent sine inverse of x. By definition, sine y equals x. So we are really using this part in essence. We are using this part, everybody. Okay, very straightforward. Okay, now we're going to work on this, and we are going to differentiate both sides implicitly. We're going to differentiate both sides implicitly, which means when I take the derivative of sine, I get cosine. And y is like g of x, so cosine y, g prime of x, or in this case, dy dx, or y prime, and x gives me 1. So one more time, sine gives me cosine, then the argument of sine is not x, it's a function of x. We need y prime or dy dx. So dy dx is 1 over cosine y. So all we have to do, figure out what's cosine y. We know that sine squared theta plus cosine squared theta is 1. This is one of those Pythagorean identities. Therefore, you can say sine squared y plus cosine squared y equals 1. So cosine squared y, that's what we want to find, is 1 minus sine squared. And cosine y is plus minus the square root of 1 minus sine squared. And in the fourth quadrant and the first quadrant, cosine is positive, so we keep the positive part only. What is sine y? I'm going to replace the sine y with x. So this becomes square root of 1 minus x squared. And now I'm going to put this instead of cosine y. And we just proved the derivative of sine inverse is 1 over the square root of 1 minus x squared. Let's do the same thing for tangent here. We know tan inverse of x equals y. Therefore, tan y equals x. And as far as the restriction for that, it's similar to the restriction for sine. Of course, the endpoints are included for sine, not here, because power 2 x equals power 2 and x equals minus power 2, as you recall, those are vertical asymptotes for the tangent function, okay, when you graph it. So we want to prove that the derivative of tan inverse is 1 over 1 plus x squared, and we're going to use this. So we said tan inverse of x is represented by y. By definition, tan y becomes x. Let's differentiate both sides implicitly. This gives us secant squared y. And then let's say this is g of x. So times g prime of x, or dy dx, and x gives us 1. So one more time. Tan gives you secant squared. Y is a function of x. You can write dy dx or y prime, or even think about it. Think of it as g of x, g prime of x. This is 1. So therefore, dy dx is 1 over secant squared y. Now, we want to replace that, and we remember there are other trigonometric properties and other Pythagorean identity. 1 plus tan squared is secant squared. So therefore, secant squared is 1 plus x squared. 1 plus x squared. So we're going to replace this now with 1 plus x squared. And therefore, we proved the derivative of tan inverse of x is 1 over 1 plus x squared. We just proved that, everybody. It's very straightforward. So we are going to move on. So y equals e to the power of tan x, tan inverse of x, and we want to differentiate this, of course, using the product rule. So let's put a raised dot in between. It's the product of fg that requires the product rule. So e to the power of 10x, the answer is itself, e to the power of 10x times 10. Any exponential, the answer is itself, times 10, because you're dealing with an exponential function, times tan inverse by the product rule. Plus, now we are, so this is f prime g. Now this one, tan inverse, we know the derivative is 1 over 1 plus x squared times e to the power of 10x. So let me write this. F prime g plus g prime f. And all we have to do, rewrite this by putting the 10 in front, this one at top of this fraction. There's really not much we can do. 10 e to the power of 10x tan inverse of x plus e to the power of 10x over 1 plus x squared. That's the final answer. y equals cosecant inverse of e to the power of x. So this is like g of x. So as you look at cosecant inverse, remember, we had for secant inverse is 1 over x squared of x squared minus 1, and for cosecant inverse, this changes to -1 over x squared of x squared minus 1. Now, 1 is the derivative of x, and we are going to change that. This is your function, let's say g of x or u. So you are going to write, instead of 1, du dx, so minus du dx, and instead of x, you are going to write u or g of x. So following that, the -1, okay, this one is e to the power of x, this one is e to the power of x times e to the power of x. This one, if you go with this format, it's easier to see. You put e to the power of x. I want you to see that we went with this format. It's the same thing as that. And you just notice these two cancel each other. Okay, and we have -1 over, this is e to the power of 2x minus 1 under the radical. So the final answer is -1 over the square root of e to the power of 2x minus 1. Okay, let's look at one more page. Last question, y equals x sine inverse of 3x, and I'm going to put a raised dot in between, meaning we are going to use the product rule. F prime g plus g prime f x gives you 1 times sine inverse of 3x plus, I want to differentiate this. And again, I remind you that for the sine inverse was 1 over square root of 1 minus x squared. If you change the x to g of x, then this changes to g prime because the derivative of x is 1. And this changes to g of x. So you can think of it this way. It may be easier to see it this way. So plus, we're going to go like that. The numerator. So first of all, this is 3x. And 1 times g prime of x. This is your g of x, okay, everybody? This is your g of x. So the answer is 3, okay, and 3x here. We're done. However, going back to the product rule, I need f. So this is g prime. Let's not call this one g. Just, if this is f, this is g. Now you need f, which is x times x. And now all you have to do is simplify. The first one is sine inverse of 3x. This one is 3x over square root of 1 minus 9x squared, and we are done. Part B, x cosine inverse of x minus square root of 1 minus x squared. We are going to differentiate, and to do so, first of all, we're going to change this to 1 minus x squared to the power of 1/2. So for that reason, we can use the power rule on that. This one is x times cosine inverse. So again, we are using the product rule. So x gives you 1. So dy dx is 1 times CD f prime g times cosine inverse plus g prime f, the derivative of cosine inverse, is -1 over the square root of 1 minus x squared times f, which is x. And I'm going to work on this. We've seen this many times before. Minus 1/2 sits in front. Same thing to the power of 1/2 minus 1, or negative 1/2. And then by the chain rule, the derivative of the inside, negative 2x. We're done with calculus. We are going to simplify, put them next to each other to see what we end up with. This is cosine inverse. It's very straightforward. This one is minus x over the square root of 1 minus x squared. Now, what is this? I hope you see that we have a plus sign here, and these two cancel each other. And what you're looking at, x over this thing to the power of 1/2. So x over the square root of 1 minus x squared. One more time. This repeats. This one is minus x over square root of 1 minus x squared. Convince yourself the brackets give us x over 1 minus x squared. And these two cancel each other. dy dx is cosine inverse of x as the final answer.